Good evening, everybody.
Good evening, sir.
Yeah, good evening. We about 14 minutes, about 16 minutes behind time. Yeah. Sorry for that little glitch. We had some technical challenge we have to face, but nevertheless, thank God we are here. So once again, good evening, everybody. Can you can you hear me clear?
Evening, sir. Yes,
Yes,
we can.
yes, sir. Good evening.
All right. I want to welcome each and every one of us who made it to be available in today's training. So we shall quickly go into what we have. For those of you joining us for the first time, I believe, are there any participants here? Is anyone here that this is your first time in participating in any of our training? Do we have such people? Maybe today is the first time in joining our training. Is there anyone here?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay. Okay. Daniel Oluboyo, is that your first time?
Yes, sir. It is my turn.
Okay. I can see Christian, your hand was up. Do you have something to say? All right. So to those whom this is their first time in joining our training, we want to say a big welcome to all our first time participants. Yes, this training is being organized by Hendeb Industries Nigeria Limited, and is always anchored through their training division, that is School of Computational Chemistry and Biology. So we are a next generation industry focusing on turning our research into products. The our society demands a lot from us, and we have decided to see a way which we can use some next generational tools to solve some of our societal problems. So our research cuts across drug discovery, um, environmental pollution control, waste management, energy generation, and other areas. So once again, we are all welcome to tonight's training. Right, I may not be sharing my slide, so it will be more like discussion because we have already had this. Let me say we had the phase one of this training last week, Wednesday. How many of us we had the webinar last week, Wednesday? I think most of us were there, just few persons, maybe those who are joining us for the first time, they were not with us in that webinar. So we are talking about predictive modeling. That is why we have gathered here, predictive modeling. And I will talk a little while we move into the hands-on practice. Professor, or rather Dr. Owolabi Rotimi, who handled the webinar session last week. Okay, Doc, let's see, your hand is up.
Yes, sir. I want to appeal to you that for the sake of those that are new, if you have a slide for us, you can share it, sir. For the sake of those that are new in our midst.
Okay. I nearly wanted to cancel this class due to my tight schedule, so I was not able to prepare a slide for it. But I will share the slide of last week because it's exactly what we are discussing, but now hands-on. So last week last week Wednesday, we did a prayer orientation. So we had all the theories. So just for the sake of those who are new today, I will share the slide with you. Yes, the slide will be part of the drive. So those who have made that commitment fee as described in our mail, the mail that was sent to you, the commitment fee of 2,000 naira for local participants and 3 USD for foreign participants. So after this class, the recording of this class will be in that drive. So you have access to all the materials, some textbooks, some publications on QSAR and QSPR modeling, and then the slide that was shared last week, and the recording. Everything will be in that drive. So I will encourage those who have not made that commitment fee to still do that. You still have time to do that, so you can have access to the video. So I will just talk a little theory because we have done that before. Just say a little thing and move straight to our hands-on. I particularly want to do more of the hands-on tonight. So we are talking about QSAR and QSPR predictive modeling. Now, when we talk about modeling, prediction, prediction means to forecast, to say what will happen in the future, to predict. Those that are into bet Nigeria, this their 1s bets or whatever, they predict. But how do they predict? They predict based on probably certain repeated occurrence. So they predict based on certain pattern. When they see a match to be played between A and B, they will not just say that A will win B just by guess. There will be a pattern which they will record. So when they record that pattern, maybe A and B has met each other before. And from that outcome, they can now, and A and B has encountered themselves more than 5 times. So that more than 5 times encounter has created a pattern. Now, that pattern can then be used to forecast what will be the outcome of the new encounter, of the upcoming encounter between A and B. So, in the whole sense, that is what we call prediction. When you are forecasting the outcome using already established pattern. Now, in the area of medicine, in the area of environmental science, and in the area of energy and other aspects which we focus, we predict the activity of a chemical species or the activity of a biological species based on a model. Now, that model is called a mathematical function. So, in science, we don't predict based on how Chelsea and Man U has played before. That one is based on pattern. You observe the pattern, and that pattern can now can help you to infer what will happen in the next outcome, in the next match. So, but in science, we now predict by creating a mathematical function, by creating a mathematical equation. So when we create a mathematical equation that can help tell us the possible outcome based on the data we have, that is prediction. So we can now call it predictive modeling, where we create a mathematical formula equation that will help us to predict future outcome. It's just like if I have an equation says 2s, s plus y equal to z. That is a simple model. So whenever that model says that for me to get z, I will add my s and y. That will always give me z. So I don't need to go to the lab to start investigating z, whereby I have a model that can tell the outcome being z whenever I add my s and y. So whatever be the value of my s and y, once I input it into the equation, I will just have my z. So this s and y can be chemical reactions, and I don't need to go to the lab to start maybe two chemicals reacting together to form z. So I don't need to go to the lab to start reacting A and B to give me z. What I will just do is that I will just create that model, that s plus y equal to z. So once I input the reagents, the chemicals I want to react, maybe HCl and sodium hydroxide, the model will just tell me the outcome without me going to the lab. So the whole essence of predictive modeling is, number one, to be able to create a mathematical function that will reduce the time and energy we invest in lab work. So we may not be going to the lab at all time, but rather we will be using the experimental data we have generated before in the lab, because lab work started long time ago. Lab work has been there since science began. So a lot of data has been generated depending on your area of focus. But since we started lab work, we have been generating a lot of data. Now, we now want to be using those data we have generated to build a function, to build a mathematical formula that will then help us predict future lab work without going to the lab again. So we can now start predicting outcome of behaviors of chemicals, behavior of proteins, behavior of enzymes, behavior of ligand, behavior of our molecules. We can now start predicting their effect, their activities, even without going to the lab. But we are going to make sure that this prediction will not be a guesswork. So we will not be doing a guesswork, but we'll be doing a scientific prediction with high precision. So I don't know if you are following me. Are we together?
Yes, sir. Yes, sir. We are together.
Yeah, we are following you, sir.
Yeah, I want to lay a very solid background. So we are not just going to develop any function and then do a guesswork. Our focus now is to develop an equation that would mimic, if possible, up to 80%. That will mimic what happens in the lab, such that if I was to do a reaction in the lab and I was to have maybe I'm doing a synthesis, and if I want to do it in the lab, I'm to have a percentage yield of 80%. Now, if I now want to do prediction, we are going to build a model such that the prediction will still give me, if possible, close to that 80% that I was supposed to have in the lab work. So we'll build a model such that the model will not just guess any value, maybe 10% or 5%. We'll build the model such that the model will mimic what happens in the lab as if that was done in the lab, such that the difference between the experimental results and the predicted results will be negligible, will not be much, the variation will not be much. So that is the kind of model, we want to build. A model that you may want to do something in the lab and you say, okay, let me use my model. Now that model will be able to give you close, very close to what you are supposed to also achieve in the lab. So that is where science have gotten to, where we no longer stress ourselves going to the lab. We will start building models. So at the end of this training, we shall learn how to build simple models. Now, most of these models are built with programming language like Python, R Studio, using R Studio, using use of deep learning, use of machine learning. But whether you are programming is not a mathematical function. I want to get this clear, because some person will say, okay, that means since I don't know programming, so I may not be able to build models. No. Whether you are using machine learning or deep learning, or you are using any tools, the principle is that they operate based on a mathematical function. So even when you are doing programming, even when you are using Python, or you are using machine learning to build a model, that model will always operate based on a mathematical function. For those who have done math and stats, those from the background of math and stats, these models we incorporate in our softwares. We are what they created with pen and paper, and then you see them solving. They'll input their variables and then begin to solve. Like, let me just use what is common to us. ANOVA is a model. ANOVA is a model that once you input your variables, it will use that model and give you the ANOVA results. But do you know that there are some professors, some lecturers will tell you, use your hand and solve that ANOVA. I don't know if you have encountered that, but I have seen a lot of students, mostly those in food science and technology, when they are doing their sensory properties, their analytic analysis. So they will always, depending on the school and the lecturer, but most often I've encountered, they will tell them, use your pen and paper, solve the ANOVA. You imagine somebody solving ANOVA of a food table. So it means that even that ANOVA that we just input our value using SPSS or SL and to generate the result is a mathematical function that people solve that was derived. So whether you're using machine learning to do modeling, that operation was a mathematical function. So if we can get that function, there, you can now use simpler tools to build it. So I understand that most of us are not into programming, but I'm saying it now that there is a training coming forth towards the end of the year. So we shall take our time to build our biomedical scientists, to build our participants on programming, because it is important in medicine, it's important in science. Every scientist should know a little bit of programming, because our life is even programmed. Our scientific world is programmed. So we ourselves, we are programmed. You program your day, you program your activity. That is programming. Now, we are not going to build simple model through mathematical functions. So if we may not have access to machine learning, to deep learning, because that will not be the scope of this training, but then we can use some of our statistical tools to build that same mathematical function and validate it. So the whole essence is for us to predict results that will mimic our lab work. If we can achieve that, which there are many models. There are different kinds of models, different kinds of mathematical function. But the whole idea is that the model must mimic laboratory work, such that you can go back to the lab and validate the outcome of that prediction. Today we are using in silico tools. In silico tools, we are all based on predictive modeling. So I've taken just a little time to see how we can have that good background on predictive modeling. So in this 2 days training, what kind of model do we want to build? We want to build two types of model. We want to build a QSAR model, and we want to build a QSPR model. That this model can be used to predict the activities of a biological entity, a chemical entity, and even environmental outcome. So that is the goal of this training. So what is QSA? Most of us have already gotten good knowledge of what QSAR is. So I will just do a little talk on it. Now, when we talk about QSAR, we are talking about a quantitative structure activity relationship. Quantitative structure activity relationship. And when we talk about QSPR, we mean quantitative structure property relationship. So one is activity relationship, while the other is properties relationship. Now, something is common between this activity relationship and the property relationship. What is common is the S, structure activity relationship, while the other one is structure property relationship. That means that the properties of any chemical entity can be related to the structure, and also the activity, which is the effect, the aftermath effect of any entity, be it biological entity, is also related to the structure. So if I have a structure of any chemical species, just with that structure, I can predict what that structure can do, what that structure can perform. That is the quantitative, means that we will quantify it in figure that can tell us how the activity of a structure. That is SAR, structure activity relationship. So we can relate the activity. I can know if my compound will possess anti-diabetic property. I can know if my compound can be able to reduce blood sugar level without conducting without conducting any glycemic analysis, without using animal models. I can know if this any structure I have. So if you can give me a structure, I can use that structure to know if that structure can inhibit cancer cells, even without testing it on any cancer cell, even without interacting that compound with any cancer cells. I will just know. That is by prediction. So how will I know? Okay, you can give me a substance and ask me, can this substance be able to remove, be able to treat wastewater as a coagulant? Can this substance act as an absorbent? Can this substance absorb heavy metal from the solution, from waste? I can know and I can tell you if it's possible based on prediction. So I don't need to go to the lab again. We don't need to waste our money. We need to start complaining that we don't have reagents. No need to start complaining that we don't have chemical. No need to start complaining of power supply. No need to start complaining of lack of technical know-how. The lab is this, the lab is that. We can now, at your comfort zone, predict if this substance can be a good absorbent. We can predict if this substance can destroy cancer cells. Can predict if this my new structure, if it can inhibit microbes. So how would that be done? We are going to look for already known data. So that is the first step now in QSAR. I think I'm going to share my screen now. So we start something. So as I'm explaining the steps, we shall be practicing them together, right? Okay, can you see my screen?
Yes,
Yes,
sir, we can.
All right. So now that I don't want to go to the lab to start doing my in vivo, in vitro, even without in silico. Of course, I cannot say without in silico because what we are doing is already in silico since we are bringing in computers. So I don't want to go to the lab to start doing in vitro and in vivo studies. I don't have that money to start doing chemical tests. What you just need to do is, let's take for instance now that I have a compound, and that compound belongs to, is a morphine. That compound is a morphine. Let me just come down to what we know. I have a chloroquine. We all know chloroquine for malaria. So this chloroquine now, I have a new compound that has similar structure with chloroquine, and I want to know if this my new structure can actually, if I can use it to treat malaria. And I don't want to go to the lab to start doing lab tests, to start assessing the in vitro efficacy, effect of this. So I want to use QSAR because that is activity. I want to see if my new chloroquine derivative, if it has effect. So activity is always effect. If it has a biological effect on the Plasmodium falciparum. Now, the first thing you will do is look for, because I said earlier that we have been doing lab work for years. So I strongly believe that some persons have also tested some compounds that look like chloroquine. So you will not be the first person that wants to test compounds that look like chloroquine or malaria. Some person must have tested compounds that looks like chloroquine on malaria also, and not just on malaria, on that same target. So it must be that same target, which is a Plasmodium falciparum. So you start looking for literatures. Start mining literatures. That is the first stage. What will what are you going to do with those literature? You're going to look for publications that reported structures that are similar to your chloroquine, because we are relating the activity with structure. So they must be of similar structure. So you check structures that are similar to chloroquine that people has worked on before on Plasmodium falciparum. You look for that information and get their activity, get their report, the result they got. So the challenge you may have is availability of data. So the first step is go by literature, mine literatures, get reports on structures similar to chloroquine and their anti-malaria activity against Plasmodium falciparum. So how can you search that? You can just search chloroquine derivatives against anti-malaria activity of chloroquine derivatives. So let's see if we can have that. So I'll just go online and say anti-malaria activity of chloroquine derivatives. So these derivatives are compounds that are similar to chloroquine. So you cannot have a chloroquine-like compounds, and then the ones you are using to build a model will now be anthraquinone compounds or quinine compounds. So the number one step is you must be able to generate similar structures that are similar to your own structure, because we want to see that if paracetamol can reduce pain, if I have a compound that also look like paracetamol, can it also reduce pain? Because it looks like paracetamol. It's just like if you see someone like Mr. Henry, and so little things about Mr. Henry. So when you see someone that looks like Mr. Henry, what do you expect? You begin to expect that person to do like Mr. Henry, because of you have built a model of Mr. Henry around your brain. So when you see anything that looks like someone that looks like Mr. Henry, you now predict the outcome of that person. So the same way, you cannot predict, you cannot see someone who does not look like Mr. Henry in any form at all, and then you expect that person to exhibit the same property with Mr. Henry. So they must be alike. They must be alike. Whether you are doing property relationship or you are doing activity relationship, they must be alike. So how do you get these compounds that are alike? I said go through literatures, mine literatures. Like what we want to do now. The first outcome now is okay. Let me pick this one. So you mine literatures. Whenever I tell students to mine literatures, they always get I don't know. There is this reaction I do receive from them, because see, if you can't mine literatures, that means you're not ready to be a researcher. You're not ready to go into research, because research means keep searching. And if you don't have that skill, mining of literature is a skill. So if you don't have that skill of mining literature, you just start looking for those skills. Start learning it. Most times there was a work I needed to do. Okay, when I started meta complexes, when I started doing a work on when I started docking meta complexes and nanoparticles, I have to look at a work for my professor, my mentor, Professor I.E. Otokure. I had to look for his publication. He has over 150 publications on meta complexes. and the activity. So what did I do? I have to search his publications, get those 150. I sat down and studied each of them. After then, I called him on phone. So you don't be, imagine calling somebody and then you tell the person that, sir, I just finished studying your publications. I had up to 150 of your publications and I'm done with them. The person said go shop. So that was what I did when I started docking meta complexes and nanoparticles. So we still have a training on that, on molecular docking of nanoparticles. Yes. So coming to this work now, if you scroll down, so we are interested in two things here: the structures and the activity. Now, the activity must be good. So this is what we need. The activity. Can you see my screen?
Yes, I can.
So this work, this stream 13 and stream 14, we are the two derivatives they use in this study. They have two derivatives, stream 13 and stream 14. And if you go up, you see those. Okay, I think those who join us in the beginners course on computational chemistry can relate very well for us here. Let me use the word they can relate. So this is stream 13 and stream 14. So this is the structure for stream 13. Your R1 is H, your R2 is N-dimethylamine O-ethyl, ethylaminoethyl. While your stream 14 is R1 becomes CH3, while the R2 becomes that same N-dimethylaminopropyl. So these were the two compounds, the two derivatives of chloroquine that was used in this study. You are going to get them. And when you get them, please take note of their IC50 value. That is the activity. So this is the activity. This is the activity we need, the IC50. And then you take note of the unit of the activity, because we want to predict the activity of our new chloroquine derivatives. So we need previous studies on chloroquine derivatives and the activity. So, but in our own compound, we don't want to go to the lab. So you are going to mine literatures. So in those literatures, you are getting two things. You want to get the compounds, then, and the activity that was recorded, the activities that we are recorded. And in as much as the compounds will look like chloroquine, the activities also must be in the same units. So take note, the activity must be in the same unit. Activity is usually, you have a IC50, that is, if it's an inhibitory activity. You have a EC50, if it is effective activity, that is activating. Then you have a KD, you have KI. So then when it comes to toxicity, we have the LC50 for latter dose and others. So, but we are not. So if you want to work with KI is also an activity, like it's a unit. That means all your data, the data that you use, will be in KI. If you want to work with KD, all the data you will use will be in KD. So if you're working with IC50, check the units of the IC50. So you must keep all their activity in the same unit. Like the one before us now is in micromolar. So if I stumbled into another data that is in millimolar, you have to go and learn how to convert the millimolar to micromolar, or you decide to keep everything in millimolar, then you now convert the micromolar to the millimolar. But you must choose one that all must be in the same unit, because we are keeping everything equal. We are keeping all parameters constant to avoid variations. So are we following?
Yes, sir.
All right, thank you. So
But
you
we are
cannot.
following, sir.
Oh, thank you for that. So you take note of these two structures now. That is where you now need knowledge of structural representation, because you are going to draw these structures. You draw it. When you draw it, you can use a came sketch to draw it, or use a came draw to draw it. So when you draw it, you generate the smart code. So what you may just work with is just the smart code, or you may not need to even draw it. You may look for the name. So in some publications, you might see the name. They might give you the name of stream 1, stream 13. Let's see if they provided the IUPAC name of that stream 13, so that you can easily use the name to pop K and then get the smart code, because what we just need is the smart code. So they're supposed to provide the name of their stream 13 and stream 14. But if that was not provided, so you have to draw it and get the name. So whichever way you want to do it, to get the name and the smart code, that is very good for you. Or okay, so let's see another paper. Let's see another paper. These two should be the same. So okay, they are the same, stream 13 and stream 14. Metal chloroquine derivatives as possible anti-malaria. This may not be, we may not need it, but let's see another paper. So you would keep doing this. At least you mine up to 50. So whenever I'm doing public training, I always give people up to 50 papers. But if I'm doing a research work, if I'm to supervise you or to look at what you are doing, then you must give me 100 papers. Yes, I believe in paper. I work more on paper. Let me see evidence of what you are doing. Because paper work is like first hand. Let it be that the people that did that work did the magic for us, but we are trusting that this paper we got, mostly if they are from reputable journals, we are giving our trust that whatever is in that paper is valid. So everything started from paperwork. All right, so let me see this one. So this is meta. We may not need this because this is a meta complex already. This one is for meta complex, but let me still see. Okay, this is a meta complex. So this is actually what we shall be discussing later on the nanoparticle and meta complexes. So we shall learn how to do this, how to do a work like this. This is platinum. You can see my cursor. This is platinum. So such work like this is what we shall learn very soon. I don't know when that training will come up, but we have it this year. We have it this year. So let me look for another one. So you just keep searching. You keep searching. You burn your data. Yeah. You burn your data. Some will even ask you to pay to be granted access. You can pay. Of course, you can pay. So this is anti-plasmodial activity and in vivo of chloroquine molecule released. Okay, let's see. So let's come down and check their own derivatives, their results. Most important to us is their results. Okay. Okay, let me just download the paper so it will be easier for us to. Okay, this is another paper. This is another paper. Antimalarial activity and mechanism of action of two novel 4-aminoprenolines against chloroquine resistance. Okay, this one is not. Well, let's see. We should 4-aminoprenolines, two novel 4-aminoprenolines. Table 1 is anti P phosphoryl activity of BAQ and MAQ determined in parallel with chloroquine. So what is the BAQ and what is the CAQ? The CQ is already chloroquine. So you're supposed to know what is that BAQ. Then this is their IC50 values, but then is in nanomolar for this paper. Yes, is in nanomolar. So it means that, just like I've said, the ones we saw before was in micromolar. I believe all of us have this science. Yeah, everybody have a bit inclined in science, so we know how to convert from one chemical unit to another chemical unit. So you also look for another paper. So this will be our assignment today. You are going to mine some papers. So you will choose. I know we're just meeting twice, but you're going to be doing some assignment. This is anti-plasmodial activity. Chloroquine molecules released with this. So let's see. That is the paper. Let's see their table. So you don't go straight to the table, the activity table. All right. So
Sir, we are not saying what you are doing again. It's only be the first table you presented. We are seeing.
But is anyone see my screen?
We are seeing the screen.
Is anyone seeing the screen up to now?
Yes, sir. Yes.
I can see. We can see the screen properly.
All right. So that will be network from his end. So you can see this also in IC50. So you can also have this compound JRI, JR2, JR3. So you look for what is JR1, JR2. They should have a structural representation of those JR1 and JR2. You just have to study the literature very well. So they even have B12 and B2. So from here you can really study it to know. Now the problem is, now see what you might see, the problem you might encounter. Let me zoom this. They did not give their names. They just drew the structure here and informed us what JR1 is. That for JR1, the R1 here is equal to R2, which is H. So that means if you want to draw this now, your R1 will be H, your R2 will be H. That is for JR1 structure. While JR2 structure, your R1 is H, your R2 is fluorine. So you pull it and draw it. So you see the importance of that training we had, the training on chem draw. So we are here to submit the assignment. We are here to submit our project. but I know God is helping you to model the 6,000 compounds. The Lord will be your strength as you continue doing that. Then GR3, R1 is now F, R2 is H. So when you do this now, you can equally even without you stressing yourself, since you need the name, you can use your paper. Actually use your paper, like on paper. Draw this structure on paper exactly very well. Then replace your R1, this R1 with H, R2 with H. If you draw it on paper, you can upload that image, you can snap it and upload that image on AI or ChatGPT. It will recognize the image and tell you the name of that structure. So since to those of you who may not have access to ChemSketch and ChemDraw, who don't know how to use it, I think you can try this way. I've done it before, and I think it worked. So you can try it. So by the time you have their names and their smile code, that will be easier for you now. Then you come back to that table. So you have a table of data. Your data will have two columns. The smile codes of those your structures and their activity. So you just create in Excel those compounds, their smile codes and their activity. So what you are doing is that you are building the data you want to use to build a model. That's the first thing you must do. Generate the data you want to use to build the model. So I've explained about using literatures. This is another literature introducing new anti-malaria analogs of chloroquine and amodiaquine, a narrative review. So this one is a review. It may not have activity, except the review includes activity. Yeah, activity from other literatures. So you study, you mine these literatures and look at that. Okay, this one is for derivatives of amodiaquine. I think there is one above. So this one is derivatives of chloroquine. These are their derivatives, gotten compounds derived from chloroquine. So you can check if they reported their activity. If they do, glory to God. So you create a column for that. All right. Do you have a question from this part before I move to another source of data? Do you have a question from this literature mining?
Hello.
Yeah, I can hear you.
Good evening, sir.
Yeah, good evening.
Yes, I wanted to ask a question because of this last paper you showed to us. In some cases, we have these, these chloroquine derivatives, and there's this group of compounds we call hybrid molecules. Okay, that is not generally a derivative, but because it's hybrided to chloroquine moiety. Will you be able to also include such ones as derivatives?
But I didn't get it clear, Prof. Sorry.
Okay. What I'm saying is that there
All
are
right. Yes, it's better now.
anti-malarials, chloroquine-based anti-malarials, but again, they are hybrids. They are hybrids. In other words, they join another molecule completely, and they use a linker to join it to chloroquine, scaffold.
Yes.
Can you also use this type of molecules as, for your study, things like this as derivatives? Can you use them as derivatives?
Yes. In as much as they were linked to chloroquine scaffold.
Okay.
Yes. So unless they don't have any attachment with that chloroquine scaffold, because most times the presence of that scaffold has influence on the activity. So, and then
in the case of linkers, really, use hybrid molecules. It might be a different scaffold entirely, different from chloroquine, but they now use a linker which may be another, kind of chemical structure to link these two together as one drug. So we call them hybrid molecules. Because I saw one of the last paper you showed before this. I saw things like linkers there, and like this. If you notice, the chloroquine, scaffold is there. We are not having some other molecules this way, So, but these ones are not really linkers. These ones are just, yes. But there are molecules that you call, linkers that join the two together.
Okay. That means there is not one structure.
Yes, it's not one
it's
structure.
not one structure.
Exactly.
You don't use such in building models.
Okay.
Yes. Yes, we don't use such a building model.
Okay, thank you very much.
Yeah, thank you, Prof. All right, that is an insightful.
Sorry, a question that also emanates from that. For those linked molecules, the molecules are linked to the chloroquine scaffold. I just want to ask, I want to be educated. Are they contributing to the biological activity of the combined drug, or they are just serving probably to improve the pharmacokinetic property of the drug? What is the essence of that linkage in those hybrid drugs?
Okay, if I may answer your question, yes, they contribute to the biological activity of the molecule. And now what happens is that, for instance, if they link a drug, it may reduce, like he was saying, it may reduce the IC50 value from micromolar concentration to nanomolars. So you'll be having most of the hybrid molecules, you'll be having, IC50 values in nanomolar, concentrations. So it is contribute massively, and that is why they actually link us. They contribute massively to the reduction of the, of the concentration. It increases the activity, reduces the amount of the concentration required to, elicit biological activity. So they are very, very powerful molecules that are used, to do that. Even they also use them for some of them, they use them as anti-inflammatory agents, anti-diabetic agents. Different ones of them, they use linkers, that can massively increase the potency of maybe an anti-diabetic drug or something like that. So yes, they control not just the pharmacokinetic properties, but the biological activity of the drug.
Right. Thank you for that answer. Dr. Otimi?
Yes, sir.
Oh, we are clear, right?
Yeah, it's clear.
Oh, thank you. Right. So, do we have any other question from this literature mining? And if you are to do this in publication, that means I don't know, cite the literatures you mined, because those data were not yours. They are someone else's data that the person spent had a money in synthesizing. Then after their synthesis, they went to in vitro and in vivo studies. So if you have exhausted your literatures, then you can leverage on databases. So another source of these data are use of database. You can use some database has already created they have created these chemical entities and their biological activities. So you can exploit them. And one of them is the common one we know, the PubChem. You can use PubChem to get these structures. You can use PubChem to get these structures. So when you use PubChem, you join it with the one you have from literatures. So that means if I'm using PubChem also, I'm going to reference PubChem. Yeah, I'm going to reference PubChem. Now, how do I use PubChem in getting this data and their biological activity? So what you just need to do is, remember our target, our goal is similar structure on the same targets. Similar structure on the same targets. So you have to type chloroquine. Once you type chloroquine, let me just say chloroquine falciparum. So once I say chloroquine falciparum, I will search. If I search, this result will it go somewhere? Okay.
It's not chloroquine falciparum, sir. The falciparum is the parasite.
Yes. I want to get results of chloroquine related to falciparum. So
Okay.
if I just say chloroquine malaria. No, my idea is I don't want to get chloroquine structure. Please, mute your mic. Or I say chloroquine malaria. Now I want to get results of chloroquine derivatives, chloroquine compounds on malaria. So that's why I'm attaching the disease to the compound, or you attach the target to the compound. Now, even if you attach the disease to the compound and that disease has multiple targets, once the result comes out, you'll now be able to filter the target you want. But to make it very easier to search, you just attach the target with the compound. Now, once the result comes out, my interest is on the bioassay. You know, I initially smiled when I typed chloroquine falciparum. There was no bioassay, but I saw some literatures, about 5 literatures. So these bioassays are the biological activities that has been performed in the lab. So you go straight, and here he's saying there are about 4,397 bioassays related to chloroquine and the plasmodium. What you need to do is you come to this relevance. We'll sort. Our interest is to get compounds that have been tested, compounds with known activity. So once you click on relevance, come down to, you see, the last 2 options is active substance. That means we need bioassays results, bioassays report that has records of substance with known activity. That is the active substance. Substances that has known activity. So do you want them to sort it by decreasing, which is according to the number of substance they contain from highest to lowest? So let me pick decreasing. So it will sort. Now, once that has been done, so these are different work. This is I've seen here too are reports by people, by researchers, and so this work is antiplasmodial activity against Plasmodium falciparum. They use a 3D7 strain. It's a very common strain in Plasmodium falciparum. 3D7 infected now species by firefly or whatever. Now, if you look at it, bioassay type should always be confirmatory. So let me zoom my screen. So I think you can see what I'm saying very well. All right. I think it's better this way. Okay. Let me come down a bit. All right. So you can see confirmatory. So always look, check on the bioassay type. It should be confirmatory. So that means that there was a confirmatory test. And outside PubChem, you can use KBL. But most times, KBL, when you search chloroquine, you end up having compounds too that are not chloroquine-like. They are not chloroquine derivatives. So you will have to start doing data cleaning. You start using Talimonto fingerprint calculation to filter off the ones that has a high variation from chloroquine. But that will be a bit stressful for you. Now, but PubChem will just go straight to give you the ones that has chloroquine derivatives. So you can also source this data in a KBL, and this is KBL. So once you take this code to KBL, I think let me just show you that. So once you take that code to KBL, you also have KBL is a chemical database also. So let me copy this and paste the KBL so you can also see how the result will be as an external data. So I paste this and I search in KBL. Yeah. All right. So I will come back to that while it's loading. Now, if you look at this, we have 94 tested substance counts, but the ones that are active are 82. That means out of these 94 compounds, 82 has known activity. Yeah, they have known molecular activity. If we come to another report, so these are several reports. These are several reports from different authors. Here has 92, but 73 had active substance. Now, most times too, from experience, you see that those compounds found in the first report are likely to even repeat in the second report and or other reports. It may appear to be similar compounds. So you can still clean them, clean the data from there. You can remove duplicates. Yes. So let's work with the first one we got. So what do we do here? You just click on it. Click on this report, antiplasmodial activity. Once you click on it, it will open up this platform. So if you scroll down, so the source was from KBL. Then these are informations you might need, the descriptions. So you can study this. Even I use PubChem for literature mining. Yeah, I also use PubChem for literature mining. I can access literatures through PubChem as well. So you can figure out that. So this is the title of the work: Discovery of Potent Small Molecules Inhibitors of Multi-Drug Resistant Plasmodium falciparum using novel miniaturized high throughput luciferase based assay. So you scroll down, keep coming down, just scroll down. So here you see some information that the standard value here, like the result they have here, the value is on micromolar. And if you look at the description, the standard type is on IC50. So it's on IC50. So that is very useful to us. So if we scroll down to this data table, so this data table now is what we need. If you look at the activity, they are showing active. That means they have known activity. And if you look at the structure, despite the complexity, they have that chloroquine-like nature. And this is their values, and the unit is in their IC50. So what we need is to get this data. We need to download this data. So how do we download this data? You just come to this download above. There are a total of 94 tested results. So you come to this download, this place here. Once you click on the download, come down. There are different options here. We have data table. All. We don't need all the data table. We have data table that are active. We have the ones that are data table with activity of less than and equal to 1 micromolar. Then we have another data table with activity of less than and equal to 1 nanomolar. So which one I want to take between these two? You have to choose one between or you pick all active. So when you pick all active, so we will see the units they will be, so that we can change those ones that we are in nanomolar to micromolar. But from this data, all the units, the standard units, once we pick all active, the standard values will be standardized value transformed to common unit, each micromolar converted to nanomolar. So the standardized units, all of them will be in nanomolar. So by the time we choose all active, they will automatically now be in nanomolar. So I would suggest you take this data table active. So it will just get the one that has a active activity. There's one that has known activity. So under the CSV, you click on save. Once you click on save, the CSV file will be downloaded and you can open it with your Excel. So once you open it with Excel, I'm opening my, all right, so you can find the SMILE code. Sorry. So you can find this one is the PubChem CID. This column is the PubChem CID. Why this column is for their SMILEs. That is telling you that they are active. So we pick the ones that are active because we choose all active, meaning that they have known activity. Then this column is for their standard value. But then this column now, this previous one is PubChem standard value, but we shall pick this one. This nanomolar, 22 nanomolar. So that is what we will pick. So I've already converted this value like 0.04 into 0.41 nanomolar. So we need their SMILE code. We need this SMILE code, and we don't need these their IC50s in nanomolar. So they will form they will be part of our data. So we are going to join them with the ones we had from literatures. So we'll join them with the ones we had from literatures. So I will just, for the sake, okay, I will just highlight this. See how we will do it now. I will highlight this, then I will also join it with this, with their smile.
Can't see your screen.
Can anyone see my screen?
Yes, we can see it.
Yes, sir.
Okay, so that will be network from screen. So I just copied both of them, and I can open a new Excel workbook. I can open a new Excel workbook and paste. So what I'm doing is that I have my smiles, and I have the IC50. Open bracket, you put the unit nanomolar. So now this data is not enough. I will go again. I will go back to another report. So you look for another report. So let's go back again, because there are about 4,397 reports. So you are going to merge their results. You're going to merge their results. You're going to merge the results. You join them together. So let's see this other one. The second report, there has 72 active counts. So still on Plasmodium falciparum. So we scroll down also to data table. So it's a very easy and smooth job. Very easy and smooth job. Now this one is with EC50. So these ones are EC50. Why could that be? Lead optimization of 3-carboxyquinoline to deliver orally bioavailable anti-malarials. Okay. I wouldn't want to join EC50 with the IC50 data, but I will just take them. Maybe that is the unit they use, or the mechanism of EC and IC are two different mechanisms. Okay, but I will not join them, or I keep that separate. So you go to download as well. You have your active table. You click and you save them. I'll also open the data. So I will look at it from here now. Once it's opened, I will see how it looks like very well. So this is it's coming up. So this is the data still in my nanomolar. So I will do the same thing. Copy the smile codes. And also copy my activities. Then I'm going to join them with the previous one that was created. So all my database files will be in one place. So I will come below the previous one and paste. So this I will keep doing. There was a question someone raised on Wednesday when Dr. Rotimi delivered that lecture. Somebody asked a question that if I could remember the amount of data we need in building model, which I said we need up to at least 1,000 data. 1,000. We need up to 1,000. Now, there are some disease you may want to work on, and some derivative you may choose, and you end up not seeing available data. But to you now, you might be using chloroquine because chloroquine is not a new work. People have been doing that for long. So we suspect to always have data available for chloroquine. You might decide, okay, let me work on lisinopril and lisinopril for hypertension. You may now go on literatures, you see that there is not even much work on lisinopril derivatives for hypertension. When it comes to databases, that will be the worst. So that is the limitation we have in modeling because of availability of real data. Real data. So even this data we are getting from PubChem, they are real life. So they are biasing, means that they are let me use the word real life data that we are generated in the lab. And that was why I encouraged us first week of this month when we had the training on chemoinformatics. I encouraged us to stop wasting our data. We have been generating a lot of data in the lab through our students, through our research work. But those data always end in A or B. Then they will end up in the HOD's office or departmental library. After 4 to 5 years, the school will use those project work to generate income, internal revenue, by selling them off to tissue paper company, who will use your data because they are using your data in that paper to turn to tissue paper. So you see the problem we have. Something happened in the school around our institutes. You know, this NED for final year students, NYC is asking them to upload their project work online. So one of the graduates, she graduated 2023, just not too far. For you to see what is happening in some schools, she lost the copy of her project, so went to the HOD's office to search for the copy that was submitted to the HOD so she can scan it and upload. Now, the report she gave me was that the HOD told her that those work has been evacuated from her office, that is no more there. They have used it for something else. Just how many years ago? 2023. And they have already used them, and they have sold those work to tissue paper company, so the school can generate money. So you see how we are selling off, wasting off our data. So and I will appreciate if, thank God, we have some departmental representatives from their various schools here. I will love if we can sort a department we are setting up. How will I even call it? That in your department you are setting up a curator. Let me use the word a curator. That person's job is to curate your data. So you mandate all your graduates, your final year students, your BS students, masters and PhD, submit soft copy of your work to that curator, so he or she can have documented data, to have those data well sorted and saved. So the department can now create database for themselves. But here we are now mining people's work while we have our own work in the library. So I'm waiting for a school that will call me, say, come to my department and mine our data. It's possible now. I can come to the department and mine your data. So which of the school here can call me to come to the department and mine their data? Those in Uniben, Ibadan, University of Ibadan. Can I come to your school and mine your data?
Uh, we have a system of keeping data. We even
So I
keep
can
some.
come.
I'm not the HOD, so I can't even speak to that. But we have
Okay.
a we already have a system. Even with the CDs you mentioned, we have a system with CDs,
That
especially
is
with the
very good
postgraduate ones.
because
Because
a problem
our
we would
problem
like
we
to
would like
clean
to
away
in
data,
the way to
but you well.
but it's well.
All right.
All right.
Now,
Now,
you can. Okay. So I just used 2 reports and I merged this data. So this is what you would do for as much as possible. As much as possible. Then after then you clean the data. How do you clean the data? Just like the way I merged these 2 files, I will just come to data. I will go to data. I will click on this data here in your Excel. Once I click on data, I will say remove duplicates. Then you are removing a duplicate from where? Is it from the smiles or from the IC50? I will remove from the smiles, so I will uncheck IC50 and leave smiles. That means I want to remove duplicates from my smiles. So most times, if you even mine, if you mine about up to 10 reports, okay, let us see what will happen in just these 2. So if I say okay, so here we have just 1 duplicate value found and removed. So 154 unique values remained. So just 1 duplicate was found here. So you go again. So it's an interesting job. It's an interesting exercise. You go again to another report. Oh, what have I? Okay, let me quickly go forward again. So you go again to another report. Let me go back. Just one. So you check another report. These 2 reports are the same. So check the 4th one. So this is 71 bioassays, 71 active count. So you keep doing this until your body tells you you are okay. So your spirit says in your rest, then you rest. But at least you need up to 1,000 data. So look at them, they have that similar structures. They all have that similar structures, and that is our target. Then you download. So you repeat, you just repeat this. Just keep repeating this. So I will just stop at this 3rd one and remove the duplicates. So I will see what could be the outcome. Hope I'm not making mistake. 252. So let me open it. Comment. I want to open that result. All right. So that is the result here. I will do the same thing. Don't bother about the CID code. There will be no need for that first because we just want to screen. So the reason why I say you should take note of the smiles because we shall use the smiles to generate the next step. That is the chemical descriptors. So that is the next step. We are going to look at now. So I will, since I've copied them, I will still paste them to where I stopped. So I'll paste them to where I stopped. I'll paste. Then let me try removing duplicates to see if there could still be duplicates again. So here, just found 2 duplicate values we have found. So just 2 duplicates we have found. All right, so I've achieved how many compounds now? I've achieved 223 compounds. So you see that it is not difficult on using using the database, but I would like us to use database. Yes, I want to subject us to torture by using literatures in your own mini project. So let's see people who can bend, who can take that stress. One will say, why will you allow us to go through this stress? Meanwhile, that was the essence of this database, to ease stress for us. So what's the next step? We have generated the data, the derivatives we want. We have gotten that. So let me take just two questions from this part before I move to the next part. If there is no question, you can just
So, combining the IC50 and EC50, does it not affect the model that we're trying to build?
Yeah, it will. It will, because it will. I said that. Why it will? Because the inhibition mechanism and the activation effective mechanism are not the same. So just keep on with your IC50. Yes. So I just combine it. But keep on with your IC50. That is, if you're working with IC50, just use one, maintain one, so that the model will not have bias. Will not be biased. Right. Any other question? Okay. So, okay, yeah. We move to the next stage. We have gotten structural data which we want to use to build this model. So what will be the next step? The next step is get the properties. You know, we are saying that, or I always say this, that whatever a structure can do, whatever a structure, whatever a chemical structure can do, it is as a result of its structure, its spatial arrangement. So whatever paracetamol can do is as a result of the chemical structure of that paracetamol. So you can put it this way, that whatever a compound can do is as a result of its structural arrangement. So whatever chloroquine can do is as a result of its structure. It's just like what we know in basic chemistry from the work done by Dmitry Mendeleev in periodic table. We have to propose a law called I think I remember this periodic law, that the properties of an element is the periodic function of its atomic number. So in that note, we are saying that any property exhibited by this element is as a result of the position in the periodic table. So element in period 1 and the one in period 5, or element in group 1 and the one in group 5 will not have the same property, but those in the same group will share similar property. Now that is to say that structure has role to play in activity. There comes the next step. We are going to generate the structural properties of those of those derivatives, because those structural properties, they are directly proportional to the activity or to the property of that compound. Now, we call these structural properties, they are called chemical descriptors. We call them chemical descriptors because we are not going to the lab, but we want to predict the activity based on the structural properties. So we still build the model also based on the structural properties. So we are going to check the properties of this structure that contributes to the activity we want. Because a compound has so many structural properties. When we did ChemDraw, we use ChemDraw to generate a lot of structural properties. Same with ChemSketch. They can calculate those properties. So, but are we going to use all of these properties? No. You look at for the ones that has influence, direct influence. Some of the properties have indirect influence. Some of them too have direct influence on the activity of those your compounds. So we'll use them to build our function. You know, a function, a model, just like I said in my introduction, that this is a mathematical formula. And every formula, we always have the input variable and the output variable. So we call the output the response, which is the activity. Why? The inputs are your variables. So the input are your S variables. Why the output will be your Y variables. For those that have a little foundation in calculus, you see that a function, we have f of s equal to this. We have f of s equal to y. That means that response y is a function of s. So we're going to get those properties that the activity is a function of those properties. So if we are looking at biological activity, because this training actually focuses on 3 activities: biological, chemical, and environmental. But for today, I'm taking us to biological activity, while the tomorrow sessions will focus more on environmental activity, because environmental goes along with chemical activity. So I'll focus more on environmental activity. Now, when we now come to biological activity now, like the anti-malaria, is the biological activity. What kind of structural properties, better to say, what kind of chemical descriptors now directly influences this biological activity? So it's here you have to do some work, because you are the one building the model. There is no law, no standard of operation. You are the one to build the model. So you will know the kind of properties, you want to use in building that model. And mind you, if the model goes wrong, you have to check what is the error. Most times you have to change your properties. So let us discuss. Let's use 10 minutes now. I want to throw it open. Let's see, because this part is so important. You have gotten your data. Now, what will be my input variables that I can use to predict my output variable? To you, let me throw this question to you. To you, what kind of structural properties do you think directly influences biological activity? It's an open discussion. Let's contribute our ideas, because this is where you have to make critical choice. The question is, to you, there are so many biological, there's so many structural properties. We are very common with the macrophoric. Okay, let me leave a macrophore here. We are very common with some of the physicochemical properties, and some of the ADMET properties. But better, let me use physicochemical properties because they are direct chemical descriptors. Like we are common with the number of hydrogen bond donors. They are still macrophobic features. We are common with the hydrogen bond acceptor, TPSA, molar weight, log P. We are common with number of rings, stereos, number, all those calculations. So to you, if you want to build your own model, to you, which of these do you think has direct influence to biological activities? So the question is open. Anyone can contribute his idea. So who is first to go? Yeah, I want. Hello, are we together?
We are together.
Yes. So let us now share our ideas together. I mentioned some of these chemical descriptors that are generated from the structure. So to you now, apart from the first people who are just joining us, new participants, we have a lot of participants who have been following us in all these trainings. So which of these do you think we can use to predict that has direct influence on biological activities?
If I'm to say something,
yes.
If I'm to say something, I will talk about the cytochrome P450 because that should have a direct influence on the biological activity where drug interaction and all that will be occurring. I would also like to bring in all this toxicity as well, because that will also have a direct effect on biological activity. If a drug is toxic, for an example, it's going to affect the liver, and at the same time, it's going to have a kind of the nephrotoxicity aspect of it also will also be there. So that is also having a direct effect on biological activity. So I will bring in that even hematological aspect of it too, because definitely it may affect the blood cells. And once the blood cells are affected, it's going to cause a lot of problem in the system. So I will consider those.
Okay, I thank God for this interaction now. Yes, but our concern is actually the structural properties that could influence the activity of that structure. Yeah, so he raised a very good point, but our concern is looking at the structural properties. Like molar weight is a structural properties. Yes, solubility is a structural property. The number of hydrogen bond acceptors is a structural properties. Then I want us to look at those structural properties that you think might have direct influence to biological activity, because we shall, whatever we agree tonight is what we shall use to build our model.
Now, I want to ask a question from your question. Are we talking about the features of these compounds that we have biological activity as it relates to the anti-malaria activity, anti-plasmodial activity? Is that the question?
Okay, you are helping me to narrow it down to anti-malaria.
Well, because we are looking at anti-malaria here, I mean, and that is the biological activity that we are talking about.
Yes,
we are talking about biological activity in general. It's going to be a very broad answer. But we are going to be talking about biological activity as it relates to anti-malaria activity based on the compounds that we are choosing. Then it will narrow further down.
Doc, you want to subject us to high tension. because I won't say that will be difficult to figure out, but let's give it a try. So let me come from what Doc just said now. Let us narrow it down to only anti-malaria activity. So don't tell us features that affect activity generally, but let's try our best to see these structural features that directly has impact on anti-malaria activity. Okay. Somebody saying electron affinity. You explain how, please. You tell us how.
If I
Thank you.
can, if I can fire the salvo, since we are looking at chloroquine-like derivatives, we will also be expecting, and we are looking at QSAR, we will also be expecting these derivatives to have a similar target or similar mechanism of action as that of chloroquine. And if you are looking at it from that angle, we'll then have to look at what is the mechanism of action of chloroquine in exhibiting its anti-malaria activity. We know that what chloroquine does is that it inhibits an enzyme called the heme polymerase. So if we are looking at compounds that have similar structure with chloroquine, we also be expecting them to be acting along that line. So we are talking about enzyme inhibition here now. So maybe from there, we can now begin to look at features of that we expect an enzyme inhibitor, to possess. Maybe I should stop here.
Okay. Yeah. So
Exactly.
yeah.
So how do we
Hello.
differentiate between vector and
Yes,
activity?
Doc is always giving us expo. So I think from that
Hello,
expo we
sir.
can explore. Yes.
Hello, sir. Good evening, sir.
Yeah. Good evening. Yeah, I can hear you, Doc.
Good evening, sir. Well, sir, I don't think I might not really be able to mention those functional groups based on their structure. But I think what we'll be looking out for is one, the basic structure of that chloro anti-malaria, that's their basic structure of the drug, and the functional groups present, and possibly the positions of those functional groups. That is what I think. We'll consider the functional groups that are present and also their positions on the structure. Since we are talking about QSAR, so I feel everything we'll be looking at, will be based solely on the structure. That is the functional groups present and their positions on the structure of the drug. That's what I think.
Okay. Let me help us to shaping this discussion so that we will be well aligned. The focus of this discussion is, let me say, structural properties that are numerical, that can be expressed in number. Like I cited example, solubility is as a result of the structure, and then that can be converted to number. So we can tell from values, maybe log p minus 5, minus 2, minus 3 can tell solubility range. Molar weight is a structural property, and then that molar weight was calculated from the structure. So in number, the molar weight can now be 500, 200, 100. TPSA, which is a topological surface area, is a property calculated from the structure. So these are kind of things we will use to build our model from those are structures. So let us now shaping our discussion. Somebody sent something in the group now. Somebody said steric strain. steric strain, PSI, and the pi bond attached. So, but this thing will be in number. So you help us to tell that a property that you think, and we'll see if we can express that property in figure. Like person just said pi bond now, so that means we can say number of pi bonds. You see it now. So instead of us to just say pi bond, we can say number of pi bonds. So we can now calculate how many pi bonds are in that structure and express it as figure. So that is our focus, numerical properties. All right, thank you.
Sorry, then
Yeah, I
I saw Abiodun up before.
No, good evening. Okay.
Yeah, good evening. Okay.
yeah
Let me
build,
attend to
building
Dr. Abiodun.
Okay, yeah. Good evening, everyone. Yeah, I think building on what you've just explained, I think it's going to be very important for, like, if we want to determine the chemical descriptor we want to use, it's going to be very important that we understand what our target is actually. Like, for instance, now we are looking at plasmodium, which we know that it affects the red blood cells. So if we want to pick, for instance, the most suitable chemical descriptor, and as you have explained that we should be able to like account, okay, if it's 200, for instance, if we are looking at molecular weight. So I think from my own perspective, I think in this case, lipophilicity of the compound will be like the most important descriptor that we should consider, because from lipophilicity, we can tell how much of the substance, for instance, the chloroquine, that we get into the red blood cells to be able to act as what our aim is. So I'm just thinking maybe that's what we should be looking at.
Okay, that's a very good one. Yes. Okay. Dane Adewole. Dr. Dane. Dr. Dane Adewole, are you still with us?
Yes, there's still another important questions that we have not answered.
Okay.
It does sometimes that a drug can either inhibit or activate. So if I'm looking for an inhibitor or activator, what are those properties that I'm to look at?
Are you releasing the bullet back to me?
It's not bullet, it's question. I'm happy.
But is that for me, or you are just suggesting? Let me know.
To the forum generally.
Okay. There's some questions where teacher go see. Okay. So Adewale is suggesting, since our mechanism is inhibition, let's look for those properties that plays major role on inhibition. So I will take it as a suggestion, as an insight for us to also look at. Yes, I won't see it as a question. Thank you, Dr. Daniel Adewale. All right. Dr. Daniel Oreke, you wanted to say something? Oreke, sorry.
Good evening.
Yeah.
I don't know. I don't know whether I've gone into a tight corner with the discussion. When Dr. Vincent was talking and Dr. Rotimi also contributed, we veered off from that discussion because from what we are discussing, the issue of structure here, we cannot use it and then be very specific to say that we are going in for only structures that are related to malaria. It will be very difficult. I don't think this will be the tool to go in for that. So I'm only raising this so that we know we've forgotten that aspect of the discussion. We are looking at the structures, not narrowing it down to the ones that only have anti-malaria activity. I think am I right with what I'm saying, Sir Doc?
Yes, you are right. Yeah, go ahead.
Okay. So that is just what is an observation because we know we were discussing along that line, and suddenly we left what we were discussing, and so we are focusing on the structure, and we can't use the structure to narrow down we can't use this discourse to narrow down the very structures that are specific for anti-malaria now. We are only looking at other properties around, like you've mentioned.
Okay. Yes.
Yeah.
I as an early career scientist, I love engaging participants in a discussion. I'm not that kind of lecturer that always talk, and the class will end like that. I love discussing with my participants. Yes, because that will help me see their knowledge, their ability. They might even end up giving you opinion that you have not imagined. They have to go and start trying that opinion to see if something can still come out from there. Just like I replied Dr. Rotimi that it's about taking us into a very high tension. Yes, because I have not thought of that dimension, but I think after this class, I'm going to look at it personally. But we have not really applied that principle of narrowing down the chemical features, the chemical properties down to a specific target, meaning checking the properties that only or that plays active role in this target. So we have not really applied that approach. The approach we know too well. And I don't think let me not say that it will not be possible, but like I said, I will just sleep over it. But then we are saying that whatever a compound can do, so we are just putting it on generally, whatever it can do. We don't want to know what it's doing. So, but whatever it can do, even if it can cure malaria, diabetes. What kind of features do you think contribute to that, to gives it that ability to do? To okay, let's say, what properties do you think will give it ability to target, to be to inhibit or to interact with a biological target? Somebody mentioned the lipophilicity, so we shall look at the lipophilicity. Is a good descriptor. Yes, is a good descriptor. So we can now look at some of the macrophoric features that we have discussed. Remember, when we had that training on macrophoric features, we said that these features directly influences the specificity or the interaction of our ligand with a target, and that target was not mentioned. Those target was not mentioned, but we agreed that these macrophoric features directly influences how a compound will interact with a target. So a target can be any target, but we mentioned some of those features. And some of those features we mentioned were the number of hydrogen bond acceptors. So number of hydrogen bond acceptor has influence on biological activity. We mentioned the number of hydrogen bond donor. It means that they have influence on biological activity. Remember, when we are even screening, for those who joined us last month, we had a 1 month training on January on pharmacology. We are able to also screen based on biological activity. We screen based on activity using ADMET properties. Some of these, yes, we had a model which we called it Hendeb model. So we used our own Hendeb model, our drug likeness model, to screen out some compounds. So those drug likeness models can also be used in building our own, this prediction model, because those drug likeness models are properties. They are properties that contribute to the effectiveness of a ligand of a drug during this interaction with a target. So we can choose like 5. Yeah, we can choose like 4, but in building a model, we advise you pick like 4 to 5 descriptors. So one can build as much model as possible using different descriptors, different set of descriptors. Then, because it's a personal work, so you are taking the best model for you. Maybe you want to do a publication, so you are checking the best model that will meet your target. And what is that? Our target. Give us a prediction that will resemble the lab work, that will mimic the experimental results. Give us a prediction that will be very close to the experimental results. So you can now build 2 or 3 models with different set of descriptors. Whichever one that gives you that the predicted value, we are very close. They are very close to the experimental values. Then that model, we have some validation parameters. So when we look at those validation, those parameters that validate, like R square, adjusted R square, Q square, the RSME. So these are some of the parameters that we calculate that will help us to tell if our model is good or not, if we can accept that model or not. We are very common with R square in graph plotting. So we say R square close to 1 means better correlation. And for those who did the correlation and regression in basic statistics. So coming back now, we can choose, because there are many descriptors now. We can just choose like 4 or 5, build this model, and see how the prediction would be. So I would suggest, from my end, I would suggest molar weights. Yes, suggest molar weights. I would suggest number of hydrogen bond donor. I would suggest number of hydrogen bond acceptor, TPSA, log P, which is for the lipophilicity, log P, molar photometer, MR. I would suggest number of rings. So some of this we can try it in building our model. Is that okay?
Yes, so that's okay.
Yeah, that's okay. I have a question.
Oh, okay, sir.
Yeah, so we are looking at general biological activity now. We are not looking at specific biological activity. Am I right?
Yes, sir.
Okay,
yes, sir.
Thank you.
Okay. But Doc, yes, sir.
Yes, sir.
I think we should devise a means of looking at specific to, like I said before, but that will be later.
No problem, sir.
I think that is the future, because I don't think if any model has been created looking at that aspect. But for us to achieve it, that means we look at the chemistry of the reference drug, then look at the mechanism of interaction, then go down to the properties of that reference drug. Then we shall use the properties of that reference drug to build our model. So we can actually look at it, but why I would like to bring it up to this general training is it will be a bit strenuous for us to capture. Okay, I can see Dr. Vincent. Go ahead, sir.
Yeah, I wanted to say that if we go back to our QSAR, QSPR, there's a relationship we said, that activity relationship, and the structure influences the activity, and the structure also influences property. So while we are doing our model, the structure, because it is the structure we are trying to model at the end of the day, device that can function for us. So if we are using the SAR, which there's activity relationship, and the structure is what is related to both the SAR and SPR, then at the end of the day, they must somehow have effect on the biological activity. So we are not really out of order. Do you understand what I'm saying? So
Yes.
whether you like it or not, by the time we really examine these descriptors you're giving to us, because now if you go back to the Lipinski rule, these are some of the things that are there in the Lipinski rule. You understand? Molecular weight is there, hydrogen donor is there, acceptor is there, TPSA is there. So all these things, log P, water ethanol, coefficient, they are all there. So these things will guide us, because at the end of the day, they will influence the activity, because we are talking of solubility. If a drug is not properly soluble, it cannot penetrate into the target and give us the desired effect. You understand? How even the hydrogen bond, number of hydrogen bonds in the molecule, they also influence its activity and then its penetration to the target. So in and out, the model, whether we like it or not, we also that is given also have effect on the activity. If not, then we are wasting our time as it were. That would be my little contribution.
Yeah. Well said, because that is just it. If at the end the model did not predict well, means it has failed. So we have to rebuild. And so we have settled on the descriptors. This is almost 10:20. Wow, 10:25. So we should be calling it to an end. So when we meet tomorrow, what we'll do is now there will be no need using descriptor calculators. I wanted us to use a padded calculator, and I already did it, but there's no need for us to start doing that. We'll just continue with our AdMet. I think AdMet can still generate those properties for us. So we'll just use AdMet and get these chemical descriptors for all the compounds we are going to use. So for the compounds we're going to use. So by the time we do that, I will now tell you the model we'll build, because they are different models. So I'll give you access to the mathematical equation of that model. They will build the model. Then, of course, one thing we know that we are going to split our data into two. So we have the training data and the test data. 70% of our total data will be our training data, while 30% will be our test data. So the essence of those test data is to, let me use the word, see if our model mimic real life activity. So it's just like we had 100 data, we have used 70 as the training data to train our model. The remaining 30, this remaining 30 now, we know the activity. Probably one of them, the activity is 30 nanometer, 30 nanomolar. But we will not close our eyes. We'll close our eyes. We are not seeing this activity of this our test data. We assume that we are not seeing the activity. They don't have activity. Let us see if this model we have built, if the model can predict the activity to be similar to the one we have. So that's what we call them test data. So by the time we see that the activity was able to give something closer to that of our training data, we shall now use that model to now do future prediction with our new compound. So that is overview of what we shall do tomorrow. Okay, I'm seeing Dr. Daniel. Okay.
Yes,
Yeah, go ahead, Doc.
I also have a question here. I know some time ago we discussed your thoughts on drug repurposing. These, what we are doing now, is there a possibility, since we've gone into literature search, and then we've discovered that some of these drugs that are like analog to this very structure we are looking at, they are also known somehow. Possibly they have activity for another element altogether. Is it possible that after discovering that they act as this chloroquine, is it possible to term it a drug repurposing? Is it possible to say that that particular drug has been repurposed for this particular element? Now, is there a possibility? Is a question.
Okay. The idea of drug repurposing is that we are using already existing drugs, and then we are defining their purpose. We are now redefining their purpose, but you must work with already existing drugs. So if you are building your model with already existing drug, then I agree that you are doing repurposing. For instance, there might be let's say that now that chloroquine was known for malaria, but we now decided to do a work with chloroquine for ulcer now, and we checked and we had some data that had activity for chloroquine derivatives on ulcer. Now, what we now determine if we are going to do repurposing is if we are able to assess some known chloroquine drugs, not exactly chloroquine again, no, but known derivatives, maybe other derivatives of chloroquine that have not been tested for ulcer. So there could be drugs similar to chloroquine that have not been tested for ulcer. If we work with those drugs in the model, like if we now predict the activity of those drugs, that means we can call it repurposing based on ligand-based repurposing. But what we are doing here is the idea we want to create here is that we want to create new analogs of chloroquine and still test it for that known activity on malaria. So since we are using new analogs, since we are predicting the activities of our new derivatives, so it's as if we are doing a de novo. So we will not call it repurposing, because the analogs we want to predict are not known drugs. But if the analog of interest we want to predict are known drugs for another target, we will not call it repurposing. I don't know if you get that explanation, sir.
Yeah, I got it.
Okay. So that is a good direction. One can also develop a work on that area, because oftentimes, if I look at repurposing, if I look at some literatures online on drug, like what you just said now, they always use protein structure-based docking for that kind of drug repurposing. They always use structure-based docking. I think I've not seen a work where they used ligand-based. There might be, but I've not come across a work where they used ligand-based docking for drug repurposing. You can develop a paper on that, and that would be a good job. That would be a gap in knowledge. So, but here we are just creating this idea of novel compounds, novel drugs. So it will even be easier. Those that join us on the beginner's course can then use their derivatives, because those students, some of the participants had to select a scaffold they wish to work with. So they can now use it and predict their activity without doing docking. And why I would prefer this part is that this one would be more accurate than your docking, because it will, if possible, if we are able to build a good model, it will predict similar result to what you get in the lab. So similar result to what you get in the lab. So even though you are going back to the lab now to validate, but the thing is that it's not taking taking note of factors that might affect the process. Yeah, it's not taking note of factors that may affect the process. But if we still want to do a work on factors that might affect the process, then we shall look at optimization, modeling, and optimization, where we use RSM. We can use RSM now to handle that aspect. So far, I want to appreciate everyone for being around in this free workshop. It's free, but it's an eye-opener and very insightful. If you look at our trainings, our free trainings for this each month, we try to relate them. We had during the first week, we had bioinformatics, how to mine and create database. When we entered the second week, we had a webinar on predictive modeling, and now we are now looking at QSA and QSPR predictive modeling hands-on practice. So we really took our time to design our monthly work, and plus that will help the students to grab some knowledge. Although we have put up a training on this, a 1 month training also on this aspect that will cover everything we have done, but that will be for the month of April. Because for the month of March, for the month of March, next month we have a training on pharmacology, molecular modeling, and docking. So the work we did last month, we are going in details to explain how to actually do this microphone. And in that training, we are bringing on different modules. Mostly, the most important aspect of that training will be this bioisostem modeling, because I mentioned about that, and we are going deeply into bioisostem modeling. We also bring in a macrophore recombination. It's something related to what Professor Vincent thought about the linkage. So it's something similar to that. Macrophore recombination. Then we are bringing in about eight macrophoric models. So the training has been power packed. Those who join us in macrognosy can testify how it was. And currently we are already on the green chemistry, and the green chemistry has been awesome. We just had 2 classes, Tuesdays and Friday, but they were awesome. So prepare to join us by March. It's starting on the 10th of March. Prepare to join us by March on if macrophore modeling. You learn how to design compounds by yourself. Compounds that can do a lot. We call it de novo modeling. Design them by yourself. The only challenge you have is the synthesis. So once again, I really want to appreciate everyone for coming. But for those who wish to have access to the materials, our culture is that in all our training, we give you textbooks, about 4 to 5 textbooks related to the training, so you can read. We provide some materials, like in this one now, I'm providing some journals, some literatures, some published literatures on QSAR 3D modeling. So you see how they are done. Then we have the recording will be there, and you have access to your certificates. So you are making a total of just 2,000 naira. So if you have not done that, you can still do that tonight, so that by tomorrow morning we'll prepare the video. You have access to the recordings, and you have lifetime access to the recording. So I wanted to give an assignment tonight, but I will skip that assignment. Let's just try what you have done by yourself tomorrow, where we'll meet again by 8 p.m. You have a project to do, a mini project to do. So while you are relaxing tonight, just think of something you can do as a mini project. All right. So we draw the curtain close here, except if anyone has something to say. And please, if you are not in the WhatsApp platform for this training, please, I will appeal you do well to either chat me up and join, because we noticed that over 50% of the participants did not follow the instruction while registering. So some of them were not in the platform. So that you not miss out information regarding the training. So at this point in time, I will bid you goodbye. Good night, everyone.
Good night, sir. Good night, everybody.
I didn't hear your voice, so.
Good night.
Good night, sir.
Good night, sir.
Good night.
Good night, sir.